All right. Well, let's take a look at the syllabus here really quick. See where we're at. Pick this syllabus. So we're at week 12 now. And so the exam I'm going to move to Wednesday here. Exam 3. And we're still in chapter 13. I'm going to finish up chapter 13 today. And so we're behind a little bit here. For tomorrow, we're going to do experiment 8. So take a look at that. We've actually already started it, and we'll continue working on that tomorrow. The last day to drop is Friday, and so the exam tomorrow is going to be mostly multiple choice with a couple of free response problems. So you'll have to draw an energy level diagram, Lewis structures, maybe a three-dimensional structure that is a molecular geometry as well. We'll look at that today. All right, so going back to this, we have a hydrogen. How many electrons? A carbon. 3 oxygens. Would be 3 times how many?
7.
Not 7. 6. Oxygen group 6. So 6 valence electrons. A -1 charge. +1 electron. So altogether we're going to have 18, 22, 23, 24 electrons. And then normally we put which element in the center of this, or least electronegative, which should be hydrogen, but hydrogen never goes in the center. We're going to put carbon. What should we bond to the carbon? The oxygens? Yeah. 1, 2, 3. Should we also bond the hydrogen? Why not? We have a rule that this is considered acidic hydrogen, and that does not bond to carbon. If it bonded to carbon, it would make it non-acidic. We'll talk about why that is later, but...
Mm-hmm. Is it a structure that looks, it doesn't look like that?
It doesn't matter how it looks. You can draw it any way you want. The Lewis structure doesn't have to accurately represent the actual three-dimensional structure. We just have to lay everything out. And so I put the hydrogen on the right, but why didn't I put it on the top? Well, I could have, or the bottom. I could have done that too. It doesn't matter. I just put it to the right. All right, how many electrons have we used? 2, 4, 6, 8. 8 out of the 24. So what do I do next? We fill up the octets to the most electronegative. In this case, we'll do to the terminal oxygens here. This is called a bridging oxygen. It bridges 2 atoms. This is called a terminal oxygen because it just ends, it terminates the chain here. So we'll complete the octets to these. That is, it'll need 3 lone pairs and 1 bonding pair. That gives us 8 electrons total around it. So I have an octet around that oxygen and this oxygen. And then we'll complete the octet to this oxygen here, the bridging oxygen next. All right, now let's see how many electrons I've used up so far. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up all 24 electrons, but I don't have any more electrons. I don't have enough electrons to complete the octet to carbon. Do you see that? And so I'm stuck with less than an octet on carbon, but there are some tricks that you can do. And one of the tricks is we can form multiple bonds to complete octets if needed. Form multiple bonds by converting a lone pair to a bonding pair. If there are not enough electrons for the center atom. If there aren't enough electrons for everybody to get an octet. And so in this case, carbon has how many? 6. It wants 8. And so what we're going to have to do is we're going to convert. But we have a choice. We can take the top oxygen, convert a lone pair into a bonding pair. This oxygen on the right, convert a lone pair into a bonding pair, or this oxygen on the bottom, convert a lone pair into a bonding pair. And so let's take a look at the 3 choices here. So choice 1 is, I'll just take this lone pair here, it doesn't matter which of the 3, and then just move it into the bond. That's choice 1. Choice 2 might be, I will take this lone pair and move it into the bond here. That would be choice 2. Or choice 3, this is in no particular order. You can do it this way. So if we go route 1, what do we form? If we go route 1, I'm going to use this lone pair over here and make that a double bond. And we end up with this structure here. If we do route 2, I'm going to leave the other 2 alone. And so this will still have 3 lone pairs there. And this one will have 3 lone pairs here. But now I'm going to form a double bond here. And then I'll do 3. Like that. And if you see what we accomplished, so if oxygen gives up a lone pair and uses it to make a bond here, we'd end up like this. Now there are only 2 lone pairs on this oxygen, but we'll have a double bond. And did oxygen lose its octet? No, it still has an octet, but what happened to carbon? What happened to carbon is now carbon has an octet. So this looks like a win-win situation, doesn't it? Oxygen still has an octet, and now carbon, which didn't have an octet, now has an octet. So win-win. but it isn't a win-win situation. Why is that? It's not a win-win situation because what has to happen is now oxygen has to share. Before it didn't have to share. Here, this lone pair belonged entirely to the oxygen. If the lone pair belongs entirely to the oxygen, what is its formal charge here on the oxygen? Well, how many electrons does it have? 1, 2, 3, 4, 5, 6, and then half the bond, which would be 7. So it has 7 electrons. How many electrons does oxygen normally have? 6. So if it has an extra electron, is it negative or positively charged? It's negative. And so this oxygen went from a negative formal charge. Now let's count the electrons here in this structure here. We have 1, 2, 3, 4, 5, 6. So it ends up with 6 electrons in this structure, but how many valence electrons did it start off with? 6. So it ends up with a 0 formal charge. Well, that's okay to do that. This oxygen, what's the formal charge on this one? Negative. This oxygen? 0. This carbon? 0. This hydrogen? 0. So the more zeros, the better. And if I sum up all the formal charges, 0 plus 0 plus 0 plus 0 plus a minus 1, I get the net charge. What is the net charge on this?
0.
The net charge is not 0. The net charge is negative.
What's unfavorable? Why was the first one unfavorable to the oxygen?
Why is this favorable? Unfavorable? This is unfavorable because of the octet. Basically, that's it. It's also the formal charges. If we go back to this structure here, do you see that this oxygen is the same? What's the formal charge on this bottom oxygen? -1. What's the formal charge on this oxygen in the middle? 0. The hydrogen? This carbon? +1. And so not only does this structure lack an octet around carbon, it also has more separation of charge than this one. This one, the formal charge has been minimized, and that's good, because the more separation of charge, that is, in this case, the second oxygen has to take the electron from carbon, the less favorable it becomes, the less stable it becomes. And so we try to minimize the number and the magnitude of the formal charge. And so the left structure looks better. How about this middle structure here? Does carbon have an octet now? Yes. How about this oxygen, the oxygen that donated a pair of electrons? Does this still have an octet? Yeah. And so, both these structures obey the octet rule, but are they equivalent in terms of energy? It turns out they aren't equivalent in terms of energy. Which one do you like better? This structure here or the previous one? In other words, 1 or 2? Which one do you like better? 1. Why? There's more difference in charge in structure 1 or structure 2? 2, yeah. And so let's take a look at the formal charges in structure 2. Okay, what's the formal charge on this oxygen? This carbon? This oxygen? This oxygen? This hydrogen? 0. So, even though we have an octet now, we have a weird formal charge scenario in which one of the oxygens has to be negatively charged. It's a negatively charged ion. But the other oxygen looks like it took an electron. So this oxygen looks like it took an electron from another oxygen. So it's oxygen versus oxygen. So is that very stable? No. And so because of the formal charges, this structure doesn't look as good. How about structure 3? Yeah, it's the same as 1, but different. And so structure 2, the charge is minus, plus 0, plus 1, plus 0, minus 1 gives us a net negative charge. So that's a net negative charge there. And then structure 3 looks the same as structure 1. The only difference is the position of the double bond. All the formal charges are 0 except for 1. And then I'll have this. When I look at structure 3, isn't it the same thing? So all I have to do is take structure 1 and then flip it or rotate it like this. Do you see if I rotate it like this, this will swing the double bond to the bottom and the single bond to the top, and I end up with this structure here. But we don't do that. What we do is we lead the atoms on the page and then see, how many choices for the double bond could we have. And in this case, there are 2 choices. In other words, there are 2 ways of making this structure, either 1 or 3. And those are equivalent. Okay, this is not equivalent. This is not going to be a stable. So we're going to eliminate structure 2. And therefore, we're going to have structures 1 and 3. Structures 1 and 3 are 2 ways of making the same thing energetically. And so what we do is we show that with a double-headed arrow here. And we call these resonance forms. Uh-huh.
What was the thing that doesn't agree with resonance?
Right.
What is
The So one of the misconceptions about resonance forms is this. Double bonds are shorter and stronger than single bonds. Actually, these 2 oxygens are supposed to be the same. Okay, the third structure, structure 2, is too energetically unfavorable, but these 2 are going to be the same energy. And so one of the things that people used to think is that the structure would just resonate back and forth. That is, double bonds are shorter and stronger than single bonds, so what people are thinking is it's resonating back and forth. That is, it's short, long, just going back and forth or resonating. And then this would be long, short, long, short. But it turns out that the 2 bonds are the same on these 2 oxygens. It's different than on the third oxygen there to the right. But the actual structure is more accurately described as a hybrid of these 2. And it's called the resonance hybrid. And so what we do is we just average these two structures. It turns out both of these bonds are the same. Rather than being a single and a double, or a double and a single, they're what we call 1.5 bonds between a double and a single. We don't necessarily have to write the square brackets here. We call those structures, the individual ones, resonance forms. This particular one would have two resonance forms. These two here. All right, so here it is. You see here, one thing we don't want to do is rotate it or change the position. Some people will think, okay, this could be another resonance form here where I have the hydrogen off to the left. And then another resonance form would be hydrogen to the bottom here, and another would be hydrogen over here. But we never do that. What we do when we figure out the resonance forms is we leave the atoms in place and then look at the different ways or arrangements that we can have for the electrons. And so we leave the atoms in place, just look at it. And so we had two choices that were equivalent. One, we could have formed the double bond on the right. That's what they did here. They formed the double bond on the right. All the formal charges are 0 except this bottom oxygen here, which is negative. Gives us our negative net charge on the outside of the square brackets. And then, resonance structures, sometimes we could have more than two, like 3, 4, etc. And all we do is we just vary the position of the electrons, not the atoms. The resonance hybrid is a species that has an actual structure that is the average of 2 or more. The average. Isomers, this is a bit out of place for this slide. These are not isomers. So, unfortunately, that shouldn't be there. They should have a separate slide for isomers. All right, so that's drawing Lewis structures. The next thing is we want to get a more accurate depiction. I could draw the Lewis structure any way I want. And so the way I drew it is fine. Here. Or the way they drew it is fine. What we want to do next is we want to figure out the geometry of these. And what we're going to do here is we're going to look at two types of geometry that we have. So I'll just use these notes that I made earlier, but we're interested in the shapes of these, a more accurate representation of the shapes. Lewis structure is not. Lewis structure doesn't have to tell you the shape. But what we can do is we can use the Lewis structure to figure out what the shape should be. And so if we're interested in the shapes of these, then the first thing we need to do is we need to figure out how many electron groups or pairs. Electron pairs is a bit of a misnomer because it could be more than one pair of electrons, pair being two. Sometimes it's only one electron, sometimes it's 6 electrons. That's considered a group. And so we look at the electron group geometry, or the EGG. The EGG gives us an indication of the shape overall and the angles of these electron groups. And then from the EGG, we figure out the molecular geometry of the MG. And this is ultimately what we want, because this is going to be the shape and the angles of the bonded atoms, or the molecule itself. From the molecular geometry, we can figure out things like polarity. You know, oils are non-polar, water is polar. What makes them polar? And we can figure out other things too. And so the electron group geometry is what we call this here. So they call it electron pair geometry, but I don't like using the term pair. I like using the term group. So electron group geometry. Because normally when we think of a pair, we're just thinking of two electrons, but it could be more, or it could be less. But anyway, it's the arrangement of electron groups around a central atom in a molecule or ion. And so electron groups. And then when we look at these groups, they repel each other because they're all negatively charged electron clouds. And so the valence shell electron group repulsion theory. If I did valence shell electron group, it would be Vess-Gur rather than Vess-Spur. But everybody knows it as Vess-Spur. Vess-Spur is a valence shell electron pair repulsion. In other words, the groups of electrons repel each other. So what they want to do is they want to separate from each other as far apart as possible. So they distribute themselves in positions around the central atom that are as far away from one another as possible. And what this is going to give us is it's going to result in an electron group angle. The angle formed by any group of electrons in a molecule or ion and the central atom between them. This is just one example, tetrahedron. This is out of place too, this slide. I think they didn't want to make a whole new slide for that, so they just put it there. So these sticks are considered groups here. And so if we have two groups, then the geometry they adopt to be as far apart as possible, or is an arrangement where they're on opposite ends of the atom. And so we'll have group A here and group B, and they want to get the maximum distance between them. The maximum distance between them will be 180 degrees. If I have three groups, then the maximum distance or separation will be at 120 degrees, and will be flat in the plane. So we give names to these electron group geometries. This electron group geometry is called linear. This one's called trigonal planar. If we had a fourth group, let's say from the top, it'll push these three down. So this fourth group comes from the top, pushes these three down. Do you know what this electron group geometry is called? Tetrahedral. And so what that looks like, those sticks look like bonds, but those sticks don't have to be bonds always. And to save time, I'm just going to reuse this so I don't, because I'm out of sync a little bit. And so I need to catch up with the morning class a little bit. So I'll just post these notes here. But electron groups don't have to be bonds, single bonds, like shown in the previous slide. In the previous slide, we had all single bonds. Atom A, some generic atom A, bonded to some generic atom B. Doesn't matter what A and B are, but we have a single bond here. Or we could have a double bond, here shown here. Or we could even have a triple bond, which is shown here. between atom A and atom B. And so each of these would consist of one group. So a single bond is one group. Some people consider a double bond to be two groups, but the problem is you can't separate the double bond into two single bonds. You have to take it as a double bond. And the same thing, a triple bond is not considered three groups. A triple bond is just considered one group. And again, for the triple bond, you can't split it up into three singles. You can't split it up into one double and one single. It has to stay together as a triple. And so each of these is considered an electron pair, quote unquote. So this is one electron pair according to Vesper. This is also one electron pair according to Vesper, and this is one electron pair. But when we look at the actual number of pairs of electrons, this has 3 pairs of electrons, that has 2 pairs of electrons. The problem is we can't split them apart, and therefore they're considered just one pair. And this is why I shy away from using electron pair. You know, I'd rather just use group. So this is one group, one group, one group. This literally is an electron pair. So if we have a lone pair, that's a pair. But we could also have a single electron. If we had a single electron, that's what we call a free radical or a dangling bond. That single electron will want to react in some way to get another electron to complete its shell or whatnot. And so free radicals aren't stable. All these are one pair or one group. I'm just going to call them one group. And so single bond group, double bond group, triple bond group, lone pair group, free radical, or single electron group. Those are the 5 different types of groups you run into. Let's take a look at the electron cloud for these particular groups here. In a single bond group, we have a pair of electrons shared between atoms A and B. If they're shared evenly, it forms a symmetric cloud like this, or a symmetric distribution. If not, then one is going to pull on the cloud more than the other, and we'll get some asymmetry in the electron cloud distribution. But nonetheless, this is one group. If we have a double bond like this, it's a little bit different. This is what we call a sigma bond here, because the electron cloud is in the internuclear region. Over here, we still have a sigma bond here. But we also have an electron cloud up here and down here. This constitutes a D or P type bond. In other words, this would be considered a pi bond. And so we have sigma bonds and pi bonds. Now, there are 4 electrons worth of cloud here, and there are 2 electrons worth of cloud here. If we have 4 electrons worth of cloud here, even though the 2 electrons in the P up here and down, up here and down here, are not in direct line here, it helps pull the A and B atoms closer to one another. And so it turns out that double bonds are stronger and shorter than single bonds. Single bonds are longer and weaker. Then we could take a look at triple bonds here. Modify this. So triple bonds will have 3 dashes there. And triple bonds are going to consist of a sigma, that is an electron cloud in that internuclear region, and 2 pi's. 1 pi is above and below. Here. Pi's are weaker interactions because they aren't direct. And so here the two nuclei are being pulled into one another. But for the pi's, it's being pulled up and down. But there's still net force pulling them together. And then we have one more pi. A double bond would stop here because the one pi is up here and here. And another pi comes out of the plane of the board and goes back in to the plane of the board. But what the point of this is we don't break it up into 3 single bonds. It's just one triple. And again, we don't break this up into 2 single bonds. It's just one double bond. And then this would be one single bond. Now, a bonding pair is split between the 2 atoms, but a lone pair belongs entirely to one atom. For example, atom A. So if we have a lone pair here, it's going to be more concentrated, at least the electron cloud, on atom A than if we had a bonding pair. A bonding pair, the atom B will be pulling on it. And if the tug of war is fairly even, this will be pretty symmetric. Here, the tug of war is totally uneven because there's no atom B. And so A gets all the electron cloud density. It doesn't have to compete with anybody. And so when we look at the electron cloud, it's highly concentrated against A here. That's where we have a pair of electrons there, and so versus a pair of electrons here. Now, a free radical would just have a single electron, so it would be less dense. As far as electron cloud goes. So let's count the groups of electrons here. If we look at this one, how many groups do we have? We have 4 single bond groups. That would be 4 single bond groups, or 4 bonding pairs. Okay, over here, we look at each carbon. This carbon here, this is for the molecule ethane, has 2 single bonded hydrogens and 1 double bonded carbon. Now the question is how many groups? So we have the single bond, the single bond. Does the double bond count as 2 groups or 1 group? It just counts as 1 group. And so altogether we're going to have 3 groups. It counts as 1 group, but there is a difference. They aren't exactly the same because what we have is we have twice as much electron cloud, but it's kind of spread out. It's not all concentrated in the sigma. We have some in the pi region too, above and below the internuclear axis. And so this is 3 groups. How about ethine or acetylene? Ethine has a triple bond here. How many groups would you count here? 2 groups. A triple bond group and a single bond group. And so this is kind of what it would look like there. We have, and this is what we do as far as counting. Like if you take organic chemistry, you'd have to count how many sigma bonds and how many pi bonds there are. And so when we look at this would be a sigma because it's right between, that would be the blue. There would be a sigma here, that would be the blue, and a sigma here, that would be the blue. So there are 3 sigmas from those, blue one. And then the other 2 bonds, we'd have a pi above and below, and then a pi in front and in back. So that would give us our pi. But for Chem 4, we don't necessarily have to worry about it so much. How about this one here? Now this one, take a look at the nitrogen. How many groups of electrons? Around this. How many groups of electrons? I see a lone pair group here, another lone pair group here, a single bond group here, and a single bond group here. And so how many groups is that? That's 4 groups. But the groups are different here because here we have 2 bonding groups and 2 non-bonding groups. The non-bonding groups would be the lone pairs of electrons. The lone pairs only get pulled one direction. Lone pairs only get pulled towards nitrogen. That's significant because what happens is if the lone pair gets pulled tighter and tighter against nitrogen, here it's going to concentrate the electron cloud on nitrogen. Versus here, the bonding pair is spread out between 2. The bonding pair is being pulled towards nitrogen and it's being pulled towards hydrogen. And so it's more evenly distributed. All right, here we have nitrogen dioxide. Nitrogen dioxide, we have a choice. We could have made the double bond on the right hand oxygen, or we could make it on the left hand. And so this first structure shows the double bond being made on the right hand. And the second structure here shows the double bond on the left hand structure here. What we'll do is we'll just pick one of these. We'll pick this one, and then how many groups do we have? We have 3 groups: single bond, double bond, and free radical. So 3 groups for this. I'm just going to break it down because the slides, there's one slide that just goes into everything at once. So we're going to separate it. Let's take a look at the EGG. Do you recall what the EGG stands for? Your book calls it the EPG. I call it the EGG. And it stands for, electron group geometry. EPG would stand for what? Electron pair geometry. But what I said about pairs still holds. So this is where your book uses the balloon analogy. So if we have 2 groups, then to separate the 2 balloons by maximum distance, we'd have to arrange those in a linear geometry with an angle of 180 degrees separating 2 groups. If we have 3 groups, then that would be like 3 balloons, and getting 3 balloons to be as far apart as possible, we'd have to adopt a trigonal planar. And the angles between each of these groups would be 120. So 120, 120, 120. If we have 4 groups, then we form a tetrahedral electron group geometry. So the 4th group, you go on top here, push these other 3 down, and then we'll rotate a little bit. And so here's the top, and these other 3 get pushed down. And then when we look at this angle, the angle 1, 4 is going to be 109. The angles 1, 3 will be 109, and 1, 2 will be 109. The 109, more precisely, is 109.48. 109.48 rounded to 3 sig figs is 109. We dropped the 4. However, if we round this to 4 sig figs, we get 109.5 because we dropped the 8 and round the 4 up. And so 109.5 and 109 are common tetrahedral angles that you'll see written. Now those are with the groups, and I just drew the groups with these little balloons here. But when we do this three-dimensionally, why is it called tetrahedral? It's called tetrahedral because if I join all the vertices with a line, I form a 4-faced polygon. The 4-faced polygon is called a tetrahedron, so this would be the tetrahedron. And that's joining the vertices. We rarely do that. What's much more common is we draw this figure. This figure has a name. Do you know what the name of this figure is? Yeah, this is called the wedge. For the wedge here, this is the wedge here. Dash. This is the dash here. Diagram. And so what the wedge dash diagram is trying to show is a more three-dimensional representation of this tetrahedral structure. And so if I look at this line here that's in the plane of the screen, this one's in the plane, this one sticks out. And so these two that are in the plane, this is a 109 angle here. And then this one that sticks out and this one that goes in is at a 109 angle. 109 angle. In fact, if you look at any of the angles, they're all the same, 109. So we call tetrahedral geometry or shape like this spherically symmetric because it's like a sphere or a ball. You know, it's as evenly balanced as you can be with a sphere or ball. All right, we aren't interested in electron group geometry. We're interested in something called the MG. The MG stands for what? Molecular geometry. And so ultimately what we want is the molecular geometry. And so the EGG gives us the shape of the electron clouds. And when we look at the shape of the electron clouds, we have to pay attention to VSEPR. VSEPR stands for valence shell, electron, pair, repulsion. I put pair in quotation marks here because I prefer to use the word group. And so mine, again, would be VSGR, not VSEPR. But what we do is we compare the electron group geometry, EGG, to the molecular geometry, MG. And so we have different scenarios here. So we could have a linear electron group geometry. And the ideal, you know what this symbol is supposed to represent? K? Or what? This is supposed to represent this angle. This is supposed to be like a compass. And so the ideal angle is 180 degrees. So we look. The ideal angle between the two groups will be 180. That way we can maximize the separation between them. And so it's going to have what we say is a linear EGG. That would be in the green. But what we want is we want the molecular geometry. The molecular geometry is the geometry of the bonded atoms. When we look at the bonded atoms, B and C, we also see that's linear. And therefore we say it has a linear molecular geometry with a BAC angle of 180 degrees. Now angles are going to be defined by three atoms, B, A, C in this case, or C, A, B. That angle is 180. Now let's try with different groups. So for example, this is two single bond groups. What if I had one double bond and one single bond group? And then the EGG is the same. And the MG, which is shown in the purple here, will be the same. And so the MG and the EGG will both be linear, and they'll both be at 180 degrees. Even though the double bond takes up more space, we don't see any distortions to this angle. Because if it pushes it this way, then the other side will push it back to its original position. We could also have a triple bond. If we have a triple bond, the triple bond is going to be the shortest and the strongest. Single bonds are weaker. And so if we look at this triple bond, the EGG will be linear. We have two groups, triple bond and single bond. And the MG will follow the same pattern, triple bond and single bond. What if we have a lone pair as one of the groups? If we have a lone pair as one of the groups, let's say we knock off C and then just make that a lone pair, then we call it a terminal atom, not a central atom. And all terminal atoms are linear, so this ends here. It doesn't bridge two atoms. All right, let me pause here. We'll take a break. Okay. Here. We have the trigonal planar EGG. And so we have three groups of electrons. Here we would have three single bond groups. But we have different atoms here. You know, the atoms might be the same, they might be different. So we have A, B, C, D. And so it doesn't matter. Let's say B and C are different sized atoms. That doesn't matter. Both of them have the same single bond group. And so we treat this as three single bond groups. If we have three single bond groups, then we want to maximize the separation or the angle between them. And so that would be 120 degrees. With these three atoms bonded to A, then we look at the molecular geometry. The molecular geometry matches the group geometry. And so the molecular geometry is 120 degrees. And so all the angles, BAC, BAD, and DAC are 120. They're all the same, regardless of the size of the atoms themselves. That's different than this case. In this particular example here, we have a double bond group and two single bond groups. And so that's three groups again. And so it'll drop the trigonal planar arrangement. But in this case, I'm going to call 120 degrees the ideal angle, because there's going to be some distortions to this angle due to having this double bond group. The double bond group takes up more space. And so ideally, we treat the three groups the same, and therefore the angles would be all 120. That would maximize the distance and evenly distribute the groups. However, since the double bond group contains more electron cloud density, that's going to take up more space. In other words, there's going to be greater repulsions. So if I have a double bond group here, I'm going to get greater repulsion between BAC and BAD. And so these go up by about 2 degrees here. And if those go up by about 2 degrees, this has to go down by about 4 degrees because all this has to add up to, all this has to add up to 360 degrees. And so we expect the DAC angle to be distorted down to 116. So in other words, this bigger group here from the double bond pushes D and C closer to one another. And so we end up with a distorted angle. The distorted angle would be these: BAC at 122, BAD at 122, and a DAC at 116. Those are just guesstimates, and so that's why I put a little tilde there. But anyway, this gives us the same molecular geometry. 3 bonded groups yields a molecular geometry of trigonal planar. The other option is if we have 2 bonded groups and 1 non-bonded group. And so let's take a look at that example here. Here we'll have 2 bonded groups, in this case 2 single bond groups and 1 lone pair. And so the EGG again is trigonal planar because there are 3 groups, and the ideal angle should be 120 degrees. However, the molecular geometry is different because when we do the molecular geometry, the lone pairs are not part of that. And so we don't pinpoint the lone pairs. We can pinpoint the atoms, but the lone pairs, we do the Heisenberg, it's uncertain. But they're there. The lone pair is there, and it's going to push D and C closer to one another. And therefore, this molecular geometry we call bent or angular. This is bent. And the ideal angle is 120 degrees. There's only one bond angle. It's the DAC angle. And we measure the angle from the shortest, not the longest. The longest would be more than 180. The shortest is less than 180 here. And in fact, the ideal angle would be 120. But we expect some distortion. We expect some distortion because lone pair is like a double bond. You know, the electron cloud is only pulled towards A. And so it's not shared. And therefore the electron cloud is concentrated here, which pushes these 2 electron clouds in. And just like in the previous example, we expect the DAC angle to be about 116 degrees. The lone pair AC angle should be 122, 122, 116. But we don't call it lone pair because we can't pinpoint that again. And so we don't call that an angle. We only call the angle between the atoms.
I'm confused. So the lone pair is what's keeping the this molecule from being 180.
Right. If this lone pair wasn't here, then it would be linear, 180. But the lone pair is there, so that's going to make it bent, not 180. It doesn't have to be a lone pair, it just has to be a group. And so let's take a look at nitrogen dioxide here and come up with a Lewis structure. And we count the groups. There's a double bond group, a single bond group, and what do we call this group? Yeah, a free radical or lone electron group. And there are 3 groups. Those 3 groups want to repel each other. That is, they want to spread out from each other as far apart as possible. And ideally, that angle would be 120 degrees. And so this would be a trigonal planar EGG, as before. A trigonal planar EGG. And so a double bond group here, a radical group here, and a single bond group here. Which is going to take the most space? Which is going to take the most space will be the double bond group. But we're going to ignore that. We're going to treat all groups as equivalent. If we treat all groups as equivalent, then the ideal angle is 120 degrees. Wait a minute. We probably can get rid of this formal charge. Do you see that? There's a problem. What's the one problem with this structure? The problem is the octet rule. Which atom's not obeying the octet rule? The nitrogen. And so one thing we might try to do with this particular structure is something like this. We'll just convert one of the lone pairs on oxygen into a bonding pair. Like that. Is that better? Well, in terms of formal charge, it's better, because what's the formal charge on this oxygen on the left? 0. It has 6 electrons, 1, 2, 3, 4, 5, 6. And oxygen has 6 valence electrons. How about this nitrogen? It has 5. It's supposed to have 5. It's 0. And this oxygen? 0. And so this is clearly better in terms of formal charge. Over here we have to separate the charges. Here there's no formal charges. So this is much better from the formal charge point of view. However, it's not good from the octet. Why? Neither are good for the octet. But this one is possible. Nitrogen doesn't have an octet. It has less than an octet. It has 2, 4, 6, 7. This nitrogen doesn't have an octet. It has more than an octet. 2, 4, 6, 8, 9. And it turns out in the second shell or second period, they say this. This is a rule. Second period or shell, second shell cannot expand their octets. Third might, so if this were phosphorus instead of nitrogen, then it's possible. Fourth might, if this were arsenic, it might. But not second. Second, it's not possible to expand. And so even though I'd like to, I can't. And so this is going to result in resonance forms. We end up with 2 resonance forms here. And that is, we leave the atoms in place, and then C. We had option A, we formed the double bond on the left. We have option B, we formed the double bond on the right. When you look at these 2 structures, they're the same in terms of energy, but they're different in terms of if the atoms were fixed in position, then we had 2 choices for the double bond. And therefore we use a double-headed arrow. Double-headed arrow like this is reserved for resonance forms. If we had 3 resonance forms, I'd draw another double-headed arrow in the 3rd resonance form, but there's only 2 choices for where the double bond can go. Even in the previous example, there are only 2 choices, even though we drew 3. Where did I put the previous example? Here there were 3 choices, but I only drew 2 because this choice here was too energetically unfavorable due to the formal charges. And so there were only 2 resonance forms here, and these 2 resonance forms were equal in terms of energy. These 2 resonance forms are equal in terms of energy. However, this is a problem because the actual structure would be thought to be what? In other words, it's not resonating back and forth. That is, double bonds are shorter and stronger. Single bonds are longer and weaker. So it's not accordion type action going on here. That is short, long, and back and forth, or long, short, back and forth. It's not oscillating back and forth. What's happening is when we do this experimentally and determine the bonds here, both bonds are exactly the same. And so a more accurate representation of the actual structure would be an average of these two resonance forms. And that we call the resonance hybrid. So the resonance hybrid is the average of all the resonance forms. So,
Why do you need to make an average for a resonance form in the first place?
Because of valence bond theory. Valence bond theory, this is what they call ad hoc. Have you heard of ad hoc? ADHOC. Ad hoc means after the fact. After the fact, they saw that it doesn't agree with experiment, and so they modified it to make it agree with experiment. And so it's a problem with valence bond theory. In MO theory, you don't have this problem. In MO theory, the structure that gets spit out after you do the calculations is like the resonance hybrid. You aren't stuck with two resonance forms in MO theory. In MO theory, you just get one structure and that's it.
You're saying that it wouldn't just be like 1/2 bonds in this case?
In this case, it's 1.5 bonds. So it's a double single, the average is 1.5. And single double, the average is 1.5. And so it's a 1.5 bond.
So it's like you want the amount of bonds that you have together, and then you divide it by
2, yeah, right. So we have these two resonance forms, both of the same structurally. And so it's trigonal planar, EGG. But when we look at the bonded atoms, bonded angles are bent. And it's going to be bent at 120, ideal. Now, lone pair, or in this case it's a free radical, takes up a lot of space. And so this may be distorted. And so this double bond here is going to push this single bond and this radical together and widen this angle here. So the double bond takes up more space. Therefore, the O-N-O angle is greater than 120. Guesstimate around 122. This is the only angle here, O-N-O. Again, we don't measure the angle between lone pairs or single electrons and bonded atoms. All right, so this is linear with 2 balloons. This is trigonal planar with 3 balloons. For linear, the only molecular geometry we have is linear. And we have a 180-degree angle. For trigonal planar, there are 2 molecular geometries. So this is showing the 2 molecular geometries. And 2 molecular geometries are going to be based on how many bonded atoms there are. Over here we have 2 bonded atoms, 1 non-bonded pair. And so here we show 3 bonded atoms. That gives us a molecular geometry of trigonal planar. Here we show 2 bonded atoms and 1 lone pair. This would be like nitrogen dioxide. There'd be a resonance form for this. But you can see it's bent. In lone pair we don't see, but it's there. And that's what's causing it to be bent. And this is going to be bent at an ideal angle of 120 degrees. However, we expect some distortion, and so the distortion will widen that angle a little bit. Now, when we go to a tetrahedral EGG, there are 3 potential MGs we have for it. If we have a tetrahedral EGG and 4 bonded atoms, then we'll have a tetrahedral MG. And tetrahedral is 109 angle here. If we have a tetrahedral EGG, but with 1 lone pair, that's going to form a trigonal pyramidal MG here. Looks like this. And finally, if we have a tetrahedral EGG with 2 lone pairs, like this, that's going to form a bent. But the difference between this bent and that bent here is this bent up here has a 120-degree ideal. This bent down here has an ideal of 109 because there are 2 lone pairs you can't see. They're compressing that angle more. So let's take a look at some examples of this. This would be NH4+, which is going to have a tetrahedral EGG. It's tetrahedral EGG based on having 4 groups, electron groups, 4 single bond groups. When I look at the angle based on Lewis structure, it looks like 90, between H, and 180 between H and H, opposite. And so if I look at adjacent, it looks like 90, opposite looks like 180. But you have to remember that Lewis structures need not be accurate. And so this is wrong. If I said the H and H angle is 90 degrees, that's wrong. If I said the H and H angle is 180 degrees, that would be wrong. Rather, the H and H angle are all the same. The H and H angle is 109 based on the tetrahedral EGG. And the MG for this would be tetrahedral. It matches the EGG of 4 single bond groups. Here we don't expect any distortions because they're all single bond groups. Now if we replace hydrogen with some other atom, let's say chlorine, then I still wouldn't expect much distortion because it's still 4 single bond groups. Maybe some slight distortion. Now what if I have 1 lone pair and 3 bonded pairs? And so the EGG is the same. It's going to be tetrahedral. It being tetrahedral, 180 and 90 aren't the correct angles. What we have to do is we have to draw out this as a tetrahedral type structure. When we draw tetrahedral, we draw it the same way, or try to draw it the same way each time. 1 in the plane that goes up, 1 that goes down right in the plane, and the angle between these, 109. And that means we're going to have 1 wedged out and 1 dashed in. This is called a wedge dash diagram. And so I did it here. The lone pair I put in the plane where this bond used to be, and I have bonded hydrogen in this plane, the same plane as the projector screen. And then I'm going to have a wedge out, that's hydrogen coming out of the screen, and the dash in, that's a hydrogen going in. And so the electron geometry is the same. I have 4 groups, that's tetrahedral, but the molecular geometry is different. Again, we don't see the electron pair here, but we do see the atoms. And when we look at the shape of the atoms, what shape is this? We call that shape trigonal pyramidal. And so it's like a pyramid with a triangle base. And so this is trigonal pyramidal. And trigonal pyramidal has an ideal angle, H and H. All the H and H angles are the same, of 109 degrees. But the distorted angle here is the lone pair takes up more space. Since the lone pair takes up more space, it's going to distort my tetrahedron here. So the lone pair takes up more space because the electron cloud is more concentrated on nitrogen. And it's going to push these other 3 down. The distortion we expect is about a 2-degree distortion from each lone pair. So that's 109 going to 107. So H and H angle of 107 degrees is our guess, this rough guess. Now, when we go to NH2 minus, NH2 minus has 4 groups. 2 bonded groups, 2 lone pairs. That's 4 groups, so it's going to adopt a tetrahedral EGG with an ideal angle of 109 degrees. And so tetrahedral, I'm going to draw this bond in the plane, this bond in the plane. That means this lone pair is going to wedge out, and this lone pair is going to dash in. So lone pairs are coming out and in. Now I have 2 lone pairs, and those 2 lone pairs here are going to be concentrated on the nitrogen, which is going to push these bonded pair in. And so each lone pair results in about a 2-degree distortion. And so I have 2 of those. That's going to result in about a 4-degree distortion. And so this distorted angle we guesstimate as 105 degrees.
How are you calculating like how much the angles are changing depending on the bonds instead of just going by the overall, like the 100?
How am I calculating how much? I'm just guesstimating it's a 2-degree distortion. And so we'll just use that. It's roughly 2-degree distortion empirically. I'm not guessing. I know what the angle is already, and so we're just using the observed distortion. It's not a prediction. Now, if we use quantum mechanics, we should be able to theoretically predict what the distortion on the angle is. But this is what we're going to call our we call it semi-empirical analysis. It's partly based on observations.
So what's causing this extra oblique angle to come down?
What's causing it is if you have a bigger balloon and you have more repulsions.
But I thought like the hydrogens were the same.
I'm sorry?
But I thought the hydrogens in that molecule were the same for each.
The hydrogens aren't causing it. The lone pairs are causing it. The lone pairs are only pulled in one direction, towards nitrogen. So if you make one of these balloons more repulsive, it's going to push the other two closer to one another. And the bonding pair are in the tug of war. This bonding pair, the nitrogen wants and the hydrogen wants, so it's in a tug of war. And what it's going to do, it's going to spread out the electron cloud evenly, or more evenly. Versus there's no tug of war. This nitrogen versus what? Nothing. Nothing's there, so nitrogen can easily win those, pull it closer. And so the lone pair are concentrated on the nitrogen, whereas the bonding pair are spread out between the nitrogen and the hydrogen. So lone pairs result in greater repulsion. All right, so those are the scenarios here. These are the ideal angles here, and we did some distorted angles here. And so we have two lone pairs here, so the angle in water should be about what? Ideally, it should be 109. Distorted, it's going to be roughly 10. There are two lone pairs. One lone pair will distort it to about 107. Two lone pairs will distort it another 2 degrees, 105. The actual bond angle in water is about 104.5. In ammonia, ideal angle is 109. The actual angle is about 107. The observed angle in ammonia is about 107. And so this is what I mean by semi-empirical. Somebody measured it first and then saw what it is and then correlated with this. It's not a perfect correlation. It doesn't always work out so well. But since they saw it was empirically, empirical observation, they didn't come up with some hypothesis saying it's going to be a 2-degree distortion. They just went out and measured it, and then they came up with an empirical correlation, which is 107 and 105. So we're going to just continue that empirical correlation. So what's this called? This is tetrahedral, Mg. This is our trigonal pyramidal, Mg, and this is our bent angular Mg. Now they're showing the tetrahedron here, the 4-sided polygon, but we don't need to show that. In geology, a lot of geologists show that because of how things link. What we do need to do is we need to show the wedge dash diagram, and we should try to show the wedge dash diagram consistently the same way. So there's a lone pair here that's not being shown, but we have the lone pair in the plane and this single bond in the plane. That means one single bond comes out, another comes in. Now what we have to do is we have to be consistent. Do you see the difference between my wedge dash and their wedge dash?
Yours has the wedge.
Mine has the wedge lower left, and they have the wedge upper left. Do you see that? We need to be consistent with whatever we do. We want to always draw it the same way. Now, when you look at this structure, tell me, is the wedge lower or the dash lower?
What?
This is the wedge because this is coming out. This is the dash. Do you see Are those two structures consistent? No. I don't like that. Here, when we look at it from this angle, which one? The wedge is below or above the dash? This is the wedge, this is the dash. The wedge is below the dash. And so, all of a sudden, and the same thing here, I think this was a problem with the graphic artist. So let's fix it. Let's see if they fixed it. And no, they didn't. And so I'm going to fix it. I'm going to put the lone pair in the plane and one of the hydrogens in the plane. That, oh, not hydrogens, this is a chlorine. Then I'm going to wedge this chlorine and then dash this chlorine here. Okay, then it's more consistent with all the rest of their drawings. All right, this molecule turns out to be just flat in the plane. It's because with three groups, single bond, double bond, three groups, it's trigonal planar. And then when we look at the bonded atoms, it's trigonal planar. So this molecule is flat. I'm sorry?
How would you not sound like a trapezoid?
Oh, trapezoid? We aren't going to have that. We're only going to have these. So this is going to be it. All right, the last section I need to talk about in chapter 13 is polarity. We could have a molecular dipole. A dipole is two poles, like a positive pole and a negative pole. And the molecules can have a positive pole and a negative pole. And for a molecular dipole, what we have to do is we have to look at the bond dipoles. Bonds can have a pole. And so what we're going to do is we're going to sum, this is sigma, the sum of the bond dipoles over 3 dimensions. This is supposed to be 3D. Sum of bond dipoles over 3 dimensions. I'm trying to show that. If the sum of the bond dipoles over 3 dimensions equals 0, then we say it's nonpolar. It equals 0 or is very small. If it's very small, that is delta En for bonds less than 0.5. These are fairly nonpolar bonds. Otherwise, if it's not equal to 0, then it's polar. And so we'll take a look at some sample molecules here. Let's take a look at carbon dioxide first. And we look at the bond dipoles. Oxygen is more electronegative, so we're going to have a bond dipole here. The arrowhead points to the more electronegative, and the positive tail less electronegative. And so oxygen is going to suck the electron cloud towards it, and therefore build up negative charge. And as it sucks the electron cloud towards it, carbon loses that electron cloud and becomes more positive. So that's the positive tail here. And so both of these oxygens are sucking electron clouds. So these bonds are very polar. However, the molecule itself is nonpolar because these are equal and opposite. So if this oxygen is pulling to the right and this oxygen is pulling to the left, they both have the same strength, so there's going to be no net movement. It's going to be a tie. If it's a tie, the molecular dipole is 0. And so what we say here is that carbon dioxide is nonpolar. If we go to boron trifluoride, come up with a structure like this. What's the problem with this structure? Boron doesn't have an octet. And so we can make boron have an octet by donating a pair of electrons from fluorine into the bond. So this fluorine ends up with 2 lone pairs when it originally had 3 lone pairs, because that 3rd lone pair was used to form this bond. Now boron has an octet, but at what cost? Well, when we look at the formal charges, the formal charges in boron trifluoride here are all 0. But if we were to form a double bond here, then the formal charges will no longer all 0. Fluorine's going to get a positive formal charge because it's donating an electron to boron, and boron's going to get a negative charge because it gains an extra electron. And so on a formal charge standpoint, this is more favorable, 0 formal charges. Not only that, which one's more electronegative? Well, fluorine is. Fluorine has the highest electronegativity on the periodic table. What is the electronegativity of fluorine? Do you know the number? 4. Boron has a significantly lower electronegativity, around 2. But what this is saying is that boron is taking an electron from fluorine. Do you think that's possible? No. If they got in a tug of war, it'd be just the opposite. No. Fluorine would be much better at taking an electron. And so we're going to eliminate this. So what we have to do is we have to live with less than an octet. Oh, that's going to make it reactive. And in fact, boron trifluoride is quite reactive. But the EGG is trigonal planar, and the MG is going to be trigonal planar. We don't expect any distortions here. All the angles should be 120 degrees. Now we look at the polarity. Fluorine's more electronegative, so it's pulling the electron cloud. But when we look at it, if there's a 3-way tug of war, which fluorine wins? None, actually. And so this is going to be nonpolar. It's not going to move anyway. And this fluorine's not stronger than these 2, etc. And so it's a tie. As is this. When we look at carbon tetrafluoride, it looks like we have 90-degree and 180-degree angles, but that's not correct. We have 4 groups. That gives us a tetrahedral EGG. And when we look at the bonded atoms are the same. And so it's an EGG and MG of tetrahedral. The angles are 109. We don't expect any distortions. And it's nonpolar because all the bond dipoles in the 3 dimensions cancel out. Actually, I didn't draw that here. Let me draw that. And so fluorine's more electronegative, so it's pulling this way. And then this is pulling down this way. Pulling down this way, and pulling down this way. And so this is what we call spherically symmetric. You know, the fluorines are evenly spread out on the inside of the sphere. So it's an even distribution. So all of these cancel out in 3 dimensions. Tetrahedral is spherically symmetric, resulting in a nonpolar molecule. So carbon tetrafluoride is nonpolar. However, if we go to this one, trifluoromethane, if we look at trifluoromethane, then this one turns out to be polar, because here these 3 are going to be pulling down, and we have nothing opposing it, because carbon versus hydrogen, the delta EN is only 0.4. The delta EN is so small, we ignore it. In other words, we call carbon-hydrogen bonds nonpolar. So, you know, the dipole for this is extremely small. It's pointed towards carbon, but it's negligible. And so net, if we have these 3 fluorines pulling out this way, the net movement will be down. And so we're going to have a molecular dipole. The molecular dipole is not equal to 0, and therefore this is a polar molecule. We show that in different ways. We could draw delta plus. So the hydrogen end of this would be delta plus. The fluorine end of this would be delta minus. And so that's our dipole. Dipole is this 2 poles, positive pole and negative pole on the molecule. Okay, any questions on that? So let's take a look at some more examples here. We said carbon tetrachloride is nonpolar. So we can represent dipoles in two different ways. We can use the deltas or we can use the arrows. Here we draw 4 arrows, all pointed towards the chlorines. And so it has very polar bonds, but they all cancel out in 3 dimensions. Here we have 1 hydrogen, so we take off 1 chlorine. And so here we're going to have a molecular dipole. The molecular dipole is going to be pointed out through the center of these. So these 3 chlorines are pulling out this way. Here we have 2 chlorines and 2 hydrogens. And so we're going to get, ignore the carbon-hydrogen bonds, those are fairly nonpolar, but we're going to get a molecular dipole this way between this two. Here we have 1 chlorine, it's going to be pulling up this way. So this is a molecular dipole for this. And here we have no chlorines, all hydrogens, and there's no dipole moment here. There's no dipole moment because carbon-hydrogen bonds are negligibly polar, therefore we call them nonpolar. And even if we were to factor in this negligible bond polarity, they cancel out anyway. But even if they weren't able to cancel out, they'd still be nonpolar. Here we can see 2 scenarios, equal and opposite. Dipoles cancel, this is nonpolar. However, this is bent. This is bent 109, and this is going to be polar. So water is very polar. There's a negative end, the oxygen, and a positive end, the hydrogen ends. And so this is a molecular dipole. These are the 2 bond dipoles here. I'll talk about organic chemistry next time. We'll have organic chemistry maybe on the next exam, I think. For this exam, or maybe I'll talk about organic tomorrow. Let's see. I didn't make a key for this, so let's go ahead. Some people were asking me for a key this morning. We'll just go through and answer these in the time we have left. Okay, number 1, stronger oxidizers to weaker oxidizers is driving force for double replacement reactions. What did you put for this? What? True or false? False? False. It's not for double replacement. Just for redox. 2, metathesis reactions consist of favorable ion combinations. True. 3, a mole of carbon-12 atoms weighs exactly 12 grams. 4, if 2 grams of hydrogen is allowed to react with excess, this is supposed to be oxygen, O2.
Solid oxygen. Solid oxygen.
No, it's not supposed to be solid oxygen. Then 2 grams of water is produced. So if 2 grams of hydrogen react, will 2 grams of water be produced? Is that true or false? It's false. 5, the theoretical yield for a reaction was 98.3 grams. The amount actually obtained was 91.5 grams. The percent yield is what?
91.5.
Yeah. Is the actual yield over the theoretical yield times 100%. So if your actual yield were 98.3 and your theoretical yield were 98.3, then that would be 100% yield. And so let's see what it comes out to. You know which one it comes out to?
Like 93.0.
Yeah, C. 6. What ions are present in what ratio in a solution of aqueous calcium chloride? C is correct.
What A has like the CO2?
What is the Cl2 minus ion called? Name this. Hmm? No, chloride is Cl minus.
Is that not CO minus?
This one, Cl2 minus, that's 2 chlorines
Looks like a substrate.
with a minus charge.
Looks like a substrate. Like it looks like a CO2.
Oh, it looks like Cl2 minus.
Mm-hmm.
Like that. What would Cl2 minus be called?
The minus goes on top, but since chloride.
All right.
Like the halogens, it tends to do.
All right. Okay. Let's put the chloride on top. The minus is supposed to go on top. What would you call that? Name that for me.
That.
What would that be called? Do you know?
Chloride?
No.
It's dichloride?
No. This is chloride, Cl minus. What would this be called?
Two of them. And it's 9.
We'd have to use analogies for this. You know what this is called? O2 minus?
Peroxide.
No, O22 minus is called peroxide. This is called oxide. Do you know what O2 minus is called? Superoxide. And so if we're to do this by analogous naming system, then we call that superchloride to be analogous to superoxide. Superoxide is not that common. Do you know why? It's so reactive. It's quite unstable. You know, each chlorine wants to get an octet, and it needs, you know, if you have one chlorine, it needs 1 electron. If you have 2 chlorines, it needs 2 electrons. But in this case, it only gets 1 extra electron.
Would it be right if it was like the charge was 2 minus? Sort of how like if you do like a mercury ion?
No. No, the chlorine doesn't do that. It likes to form like this. So if you have sodium chloride is not Na2Cl2. Sodium chloride is just NaCl. 1 sodium ion, 1 chloride ion in that ratio. Well, let's look at number 7. Weak acids are weak electrolytes. True? HF is completely ionized in water. Oops. 8. What did you get?
I need a charge.
Hmm?
I need a charge.
True or false? Hmm? False? Yeah. Why?
Probably really need to decide.
It's false is correct. Why? Hmm? Because it's a weak acid. We have the 7 common strong acids up there. Is HF one of them? No. HF is a weak acid. Which of the following substances will precipitate from an aqueous solution? From an aqueous solution. Do group 1 salts precipitate?
No. No.
No. Do acetate salts precipitate?
No, it's all
Do carbonate salts precipitate? Yes, except for group 1 and ammonium, but copper is not. It's copper 2. In the combustion of methane, according to the equation, how many grams of water are formed during the combustion of 4.24? This should be 4.24 grams of methane.
That sounds like something.
So this is just a straight stoichiometry problem. So I'll go from grams of methane to what? Moles of methane. So 4.24 grams of methane. And the molar mass is 1 mole of methane weighs 1201 plus 404 is 1605. 1605 grams. This pen is, because I'm so zoomed in here, and as thin as it's going to get. And then moles of methane to moles of what? To water. They're asking us how many grams of water. 2 to 1. 2 moles of water for every 1 mole methane. Then what? And then the molar mass of water. What is the molar mass of water? 18.02 grams. Mole. All right, let's see what it comes out to. 4.24 divided by 16.05. What is that? 9.52. The correct answer is not there. What's the closest answer? E, 9.51. Let's just hope this is due to...
Rounding.
Yeah, rounding. Okay. 11. PCl5, phosphorus pentachloride, can be produced by the reaction of PCl3, phosphorus trichloride, and chlorine, which yields PCl5. What mass of PCl3 must be used to produce 127 grams of PCl5 if the percent yield is 84.8%? Percent yield is going to be 84.8 grams over 100 grams. 84.8 grams of what? 84.8 grams of actual yield over 100 grams of theoretical yield. All right, so we're just going to use dimensional analysis for this. We'll start off with 127 grams. That 127 grams is what? Well, it's PCl5. And then we have to ask ourselves, is that PCl5 actual yield or theoretical yield? Actually, this is going to be actual yield. Why actual yield? Is because must be used to produce. So they want us to produce 127 grams of actual yield. And then we're just going to use dimensional analysis here. For every 100 grams of theoretical yield, we have 84.8 grams of actual yield. That gives us grams of PCl5 actual yield. Yeah. And then we're going to have to calculate the molar mass of PCl5. So let me do that. Phosphorus is what, 30.97 or 98? 30.97. So 30.97 plus 5 times chlorine. 5 times chlorine. Chlorine's 35.45. 185.43. One mole. Actually, I need to blow this up more. Otherwise, it's too hard to read. One mole of PCl5 per 185.43 grams. And then we're going to go to PCl3. It's a 1-to-1 mole ratio. So 1 mole of PCl3 for every 1 mole of PCl5. And then I need the molar mass of PCl3. So 30.97 plus 3 times 35.45, 137.32. So this should give me grams of PCl3. This is moles of PCl3. Oh, this is not fine enough. But anyway, let's do the calculation. So this is going to be 127 times 100 divided by 84.8 divided by, what was this number again?
1 mole over 185.
185.43. It's a 1-to-1 mole ratio times 137.32. And what do I get? Did somebody get it? Let me try punching it. I got 110, but 110 is not one of them, and that's not due to round off. That's too far away from D. So if I get 110, D is 108, I'm still not convinced that's correct. So 127 times 100 divided by 84.8 divided by 185.43 times 137. Did you guys get it?
I got the same thing, 110.9.
110.9. All right, let me double check my calculations for the molar mass. 98.8. Yeah. I don't know. I got C this morning also. But right now I'm getting 111.
What happened? So when we did the dimensional analysis of actual yield at the very beginning, what happened to the theoretical yield?
This is the theoretical yield is what we're calculating here. We're working backwards. And so the theoretical, let's say you want 127 cookies. But out of every 100 cookies you bake, you only get 84.8 because the others are either you accidentally drop them or you eat them or you give them away. And so this is what we're doing. We got to make more cookies than 127. How many more cookies do we have to make? Well, for every 84.8 that we want, we got to make 100. And so this is working backwards from that. So I'm not sure. I did some kind of thing here.
You just put the wrong one max for
Which one?
PCL5.
PCL5?
Instead of 185, it should be 208.2.
Oh, okay. That's 5 times 35.45 plus 30.97. Yeah, 28.47. That's just it. So 208.47. Okay, then it works. Does it?
It should be 208.22.
208.22? It depends. How many decimal places did you carry it out to? Did you do 30.97?
Yeah.
And what did you use for chlorine?
I used 35.45.
Oh, really? I don't know. Sometimes when I punch numbers in here, it doesn't register. Oh, it's okay. You got what? 22C? Okay, we'll go with that. Looks correct. I'm curious what I did this morning. Let me see what I got this morning. I don't know why my pen went a little finer. I got 208.23 this AM. But whichever. And so I end up with 98.77, which is C. Okay, let's take a look at number 12. Actually, I'm running out of time here. So we'll just look at this one. Here I have a little bit more space. So I didn't have to blow it up as much as I did here. But when I look at number 12, I have delta H. Is that exothermic or endothermic? This is exothermic. And so this is delta H is minus 2.82 times 10 to the third kilojoules. And this is for the reaction as written. What that means is minus 2.82 times 10 to the third kilojoules for every 1 mole of glucose, for every 6 moles of O2, for every 6 moles of CO2, and for every 6 moles of water. And so how many grams of glucose must be metabolized to produce 282 kilojoules worth of energy? So the minus means energy is being produced. And so we get 2.82 times 10 to the third kilojoules of energy lost for every mole. That is produced for every mole consumed. Or we can put this in words. Energy is always positive, and the negative just tells us the direction. So this is 2.82 positive times 10 to the third kilojoules produced per mole. We want 282 kilojoules to be produced, so we're just going to use some dimensional analysis for this. So 282 kilojoules, and there's 2,820 kilojoules per mole. And so this is actually 1 over 10. Is that? No, a little bit more. And then that gives us moles of glucose, and then the molar mass of glucose is 180.1. You can't read my writing there. 2 or 1.8? Is that 1.8? Oh, I calculated over here. It's 1.8. 180.18. soon as possible. And so this gives us 18.01 grams of glucose, which is A. Well, let's continue this. Visible light is a very small part of the entire electromagnetic spectrum. Is that true or false? True. Most of the electromagnetic spectrum is invisible. Radio waves always move slower than gamma rays. It's actually false. Radio waves move the same speed as gamma rays. They're both light. Yeah. And the speed is the speed of light.
So, like, because they all move at the speed of light, right? So if it was like infrared and gamma rays, it would still be true. But if it's like a question asking about wavelength and frequency, then it could be like true or false.
The speed, all of them move at the same speed. So regardless of which two I chose, they're going to move at the same speed. The wavelengths will be different. That's one of the, and the energies of the photons, the particles of light. Radio waves have longer wavelength. Gamma rays have shorter wavelength. Gamma rays have higher frequency. Radio waves have a lower frequency.
Do you need to know particle theory?
Do you need to know wave-particle duality?
Yeah.
Not a bad idea to know that.
Is the concept?
No, just conceptually. That was important in understanding why electrons were quantized in atoms.
I was just like, particles can behave like waves, and waves can behave like particles.
You're right.
So I know.
Right. All right.
I can connect.
That's enough, probably. Oh, I wasn't meant to save this. I was supposed to save this as. Within a continuous spectrum, there are regions of forbidden energies. That's false. We have two types. We have quantized and continuous, or continuum. If we have quantized, then they're going to be forbidden. If we have continuous, all are allowed. Incandescent light bulbs produce a line spectrum. Line spectrum is quantized. Do incandescent light bulbs produce a quantized spectrum? No, this is the hot metal. And so this is supposed to be true or false. So this is false. Light bulbs, incandescent light bulbs produce white light, and white light consists of all the colors of the rainbow. And so we have a continuum of colors.
The work didn't make up to chapter 13, right?
17. Modern day scientists visualize electrons orbiting the nucleus in a circular orbit. It's false. 18. Heisenberg uncertainty principle means we visualize the electron position as a cloud. 19. Orbitals are the solution to the Schrodinger equation. So this is wrong. It was supposed to be a different set of answers for this. Schrodinger. When L equals 1, we have the 3 p orbitals. This is false. We have the p orbitals, but this is n equals 3. And there's nothing. It could be n equals 1. No, it can't be n equals 1. It could be n equals 2, 2p, n equals 3, 3p, n equals 4, 4p. All those will have L equals 1. 21, n equals 0 is the lowest energy level. That's false. What is the lowest energy level? N equals 1. 22, 2D orbitals violate quantum mechanics because L is too small. True? Actually, 2D orbitals violate quantum mechanics because L is too big. What's the max L? Max is n minus 1. What is n? It's 2. 2 minus 1 is equal to 1. So the max L value is 1, which is a p orbital. Not D.
Why is that considered too big and not just part of the... Why is that considered too big and not just part of the theory?
Why is it considered too big and not just part of the theory?
Yeah.
You could say it's part of the theory, but what specifically about the theory does it violate? It violates the math of the Schrodinger equation. If you tried to plug in an L equals 2, which is d orbital, with an n equals 2, it comes out false. It comes out. See, the Schrodinger equation is a mathematical equation itself. And in order for us to figure out what the allowed states are, it has to satisfy the rules with the numbers. And so that would be called a forbidden energy. We don't know, we don't know it in this class because you don't have the equation. How many orbitals are there? Infinite. And so what do? Are you going to memorize all of them? No, it's impossible to memorize all of them. And so do you know what you do? You look for a pattern. And this pattern is a very good pattern. This pattern is not a rule. This pattern makes a law. And this law is based on the Schrodinger equation. This is the Schrodinger equation law. And that's the pattern that we're going to observe. And if it doesn't fit that pattern, then it's forbidden. If it fits that pattern, it's allowed. So how many forbidden states do we have? We have an infinite number. Do you want to tell me every single forbidden state? You could say, okay, if n equals 1, then L equals 0 is allowed. But L equals 1 is forbidden. Well, what about L equals 58? Is that forbidden too? Do you have it memorized, or do you have the pattern that tells you, hey, wait, that's forbidden? What about L equals 1,563,228? Is that allowed or is that forbidden? And so what we do is we use the math to tell us what's allowed and forbidden. And otherwise, you could say, oh, okay, 1,523,258 is not allowed because of the quantum mechanics. But what about the quantum mechanics makes it forbidden? What about it makes it forbidden is the math in the quantum mechanics makes it forbidden. It doesn't satisfy the Schrodinger equation. Okay, 23. The electron configuration for chromium is 4s2 3d4. This is a true-false also. Is that true or is that false? It looks true. It does look true because here we have argon. we fill the third shell, and then we start on the fourth shell. Forest 1, Forest 2, 3D1, 3D2, 3D3, 3D4. So it does look argon, Forest 2, 3D4. It looks true, but yes, it's false. What is the correct electron configuration for chromium? Forest 1, 3D, 5. It's one of the exceptions we just have to remember. 24. Hund's rule states orbitals of the same energy should be filled singly with parallel spin. That's true. 25. The electron configuration for the fluoride ion is helium 2s2 2p6. This is true also. Helium fills the first shell, and then the second shell would be 2s2, and then 2p1, 2p3, 2p3, 2p4, 2p5. So fluorine would be 2p5. However, fluoride has an extra electron, and that would be 2p6. Fill up the second shell. So the first and the second shell are filled. Tungsten. What symbol is tungsten? W. Tungsten is what they make incandescent light bulbs out of. A very high melting point. How many electrons does tungsten have? Well, let's take a look at the periodic table here. $74. Right here. 74. So we're at 74 electrons, so let's back up. We'll start off with xenon. So it would be xenon. And then here. What is this one? 1, 2, 3, 4, 5, 6. This would be the 6 shell. 6s1, 6s2. And then where would we go? 5d1, and then where would we go? No, take a look at 57. Where's 58? 4f. 4f 14. And then from 4f14 we go back up here to 5d2, 5d3, 5d4. What's missing here? The 4f are missing. In fact, when we look at it, this is 54 electrons. 54 plus 2 is 56. 56 plus 4 is 60. This is 60 electrons. Tungsten has 74 electrons. So we're missing 14 electrons. And so this will be false. True. False. It's false. Which bond is the most polar? HO? Correct. The charge on alkaline earth ions is 2 plus. Noble gases are highly reactive. The bond between a metal and non-metal is likely what? Ionic. What is the predicted bond angle in CO2? 180. Strong bases ionize in water. Actually,
Wait.
bases hydrolyze in water. They don't ionize, so this is actually false. Think of ammonia in water. Does ammonia ionize? No. Ammonia hydrolyzes, meaning it reacts with water. What is the predicted bond angle in H2O? I'm sorry? 109. This is the ideal. I should say, what is the predicted ideal bond angle? The distorted angle is about 105 because they're two lone pairs. What is the predicted bond angle in SO2?
False.
It's supposed to be a double bond here. Not a triple. What do you see? No. $120. It's 120 because if you have three groups, single bond, lone pair, double bond, that's three groups. And three groups that's spread apart as far apart as possible is 120-degree angles. What is the shape of ammonia? Which one? B or E? E or B? What did you guys say? E? Yeah. Trigonal pyramidal. CF4 is a polar molecule. False. CF4 is nonpolar. H2O is a polar molecule? True. 38, this is earlier chapters. Is this already tested you on? All right, next. It's this. For the reaction, magnesium plus hydrochloric acid yields magnesium chloride and hydrogen gas. What is the theoretical yield of hydrogen when 32 grams of magnesium is allowed to react with 24.3 grams of 7.00% by mass HCl? How much excess reactant remains? So what type of problem is this? Yeah, this is a limiting reagent problem. And which method do you prefer, the smaller amount method or the comparison moles method? Smaller amount method. Me too. So 32 grams. So first part, we do 32 grams of magnesium and we assume excess HCl. And we'll calculate the yield. And so that's 32 grams of magnesium, and then we're going to convert that to moles. The molar mass of magnesium is 24.31. That gives us moles of magnesium. From moles of magnesium, we'll go to moles of hydrogen. We want to know about how much hydrogen is produced. And so it looks like it's a 1-to-1 mole ratio. So 1 mole of hydrogen is produced for every 1 mole of magnesium. Oops. And then where do we go next? Yeah, we go from moles to grams. The molar mass of H2 would be 101, but that's only 3 sig figs. I like 4 sig figs, so I'm going to use 1008 times 2. 1008 times 2 is going to give me 2.016. 2.016 grams of H2 per mole. All right, and so that should give us how many grams of hydrogen are produced. So this is going to be 32 divided by 24.31 times 2.016. And I get 2.653. All right, B, we're going to use 24.3 grams of 7.00% HCl. And here we're going to make the opposite assumption. We're going to assume excess magnesium. So here we'll take 24.3 grams of solution. And this solution is going to contain 7.00 grams of pure HCl for every 100 grams of solution. All right. Then where? Okay, then the molar mass of HCl. 1 mole of HCl, pure HCl, weighs 36.46 grams. And then we're going to get 1 mole of H2 for every 2 moles of HCl. And then we're going to have 2.016 grams of H2 for every mole of H2. All right, so let's take a look. 24.3 times 7 divided by 100 divided by 3646 divided by 2 divided by, or not divided by, multiplied by 2.016. And I get 0.04702 grams hydrogen. So which reagent produces the smaller amount? The HCl. And so that means this is the theoretical yield. The smaller amount is the theoretical yield. And that means this is the limiting reagent. And this must be the excess reagent here. How much excess reactant remains? And so that will be the next calculation we'll do here. Excess magnesium remaining. The excess magnesium remaining is equal to the initial amount, 32 grams, minus the amount consumed by the limiting reagent. Okay, so this is going to equal 32 grams, the initial amount, minus the amount consumed by the limiting reagent. The amount of limiting reagent is 24.3 grams of solution. And then we know that for every 100 grams of solution, we have 7 grams of HCl. And then we know that 1 mole of HCl weighs 36.46 grams. And then we know that every mole of magnesium requires 2 moles of HCl. Okay, and then magnesium molar mass is 24.31. Okay, so I get 24.3 times, let me do that again, 24.3 times 7 divided by 100 divided by 36.46 divided by 2 times 24.31.56. So we start off with 32 grams. We're only going to use up half a gram. We're at 0.567 grams. $31.43 grams. 31 grams. We're only allowed no decimal places, so we'll just round this. 31 grams. All right, so that's the 3 calcs we do for this particular problem. Draw a detailed orbital energy level diagram for chromium. So this is, just have to memorize this. What's the lowest energy orbital? Or the 100, and then 2s or 200. And then we have the 2 p's, 2 1 negative 1, 2 1 0, 2 1 1. And then what comes after the 2 p's? 3s, 3 0 0. And then after the 3s, 3p. 3 1 negative 1, 3 1 0, 3 1 1. After 3p comes 4s, 4 0 0. And then after the 4s comes 3d, 3 2 negative 2, 3 2 negative 1, 3 2 0, 3 2 1, 3 2 2. After the 3d come 4p. 4 1 negative 1, 4 1 0, 4 1 1. All right, you should be able to draw the energy level diagram through the 4th shell and then fill it with electrons. 41 is do HCO3 minus. We did the Lewis structure for this, including the resonance forms, but we didn't do the electron geometry, EGG, nor the electric geometry. So we could take a look at that later, or you can do it at home. Are we out of time now? Or do we still have 5? Do we have 5 minutes, or is this it? We're done? All right.